It is 12:30, so I'm going to go ahead and take roll. For those of you on Zoom, I'm going to need you to actually speak up when your name is called. Grant Amerson.
Here.
Thank you. Garrett Anders. Oh, sorry, that's the later thing. Brandon Ashlock.
Here.
Jacob Bouton.
Here. Here.
Wade Burton. Thank you. Claire Cazadesis.
Here.
Chandler Davidson. Thank you. Juliana Damari.
Here.
Cameron Dreyer. Brooke Edmondson. Julia Everett. Jack Foyle. Garrett Gresham is here. Daniel Hill. Thank you. Brian Joes. Cade Leo.
Here.
Jacob Matthews. Dylan Miller. Noah Perkins. Alexander Petty. Nicole Robles.
Here.
Tristan Sharp.
Here.
Joseph Saharath. Kinsley Spadafora.
Here.
Thank you. Sophia Urbina, got you over there. Race Wickland. Thank you. Michael Martin.
I'm here.
And Kendra Hayward.
Here.
All right, so the first thing that I would like to do is talk about the exam. So how many of you guys have noticed that I put your scores up on our courses Moodle page? All right, great. So at least several of you, if you haven't, take a moment to go look at it. The overall score was a 63.77%. That's among all of the Engineering 221 students. In our section, the average was 60.56%, with a minimum score of 27, a maximum score of 105. In our section, only 2 students made A's, 5 made B's, 7 made C's, 11 made D's, and 23 made F's. So I want to talk about this because in my opinion, that was probably the second easiest test I've ever created for this class. And the average in this class, in this section, is literally half a point above an F. So what I want to ask of you guys is what I could be doing better or what I could be doing different to engage you more and to help you be more successful on exams 2 and exams 3. Any comments or anything like that? Sorry, speak up, please. More examples, okay. I don't have any issue with that whatsoever. It's going to be a little bit rough on the days that we have the lab assignments, which there are still 4 more of those throughout the remainder of the quarter. So to that end, if you want more examples, do you want me to work more here while I'm in class with you, or do you want me to post videos of further examples? Okay.
I was going to say, I kind of like the idea of even posting examples. I think one of my main issues is I can definitely do the concepts, but in practice, if it seems more difficult than it actually is, I just get lost. So like the in-class assignment, sometimes there's one super easy one, and then there's one that looks really hard, even though it's not necessarily hard. if we can work, if you could even do examples that are more related to ones that look a little bit more in depth than they appear, kind of thing.
All right, so I think then generally speaking, people would like both more in-class examples as well as more online examples to help them out. Am I reading the room correctly? Okay. Yes, sir. 105. So those five, so let me explain. Okay, so there are 105 possible points, but it's out of 100, meaning that there's a built-in bonus for each exam. Okay, so on Moodle or whatever, it can't, or I don't know how to make it handle bonuses. So it says that it's out of 105. Having Moodle set up to include the fact that your lowest test score only counts for half and this, that, and the other is just a hot mess of stuff that I don't know how to do. So the grades that you see on Moodle, put them in a spreadsheet and calculate your grade, based on the rubric that's in the syllabus. Yeah, there you could potentially score a 105 on the exam, which would mean that you are getting extra credit. That is correct. And then my other question is, so the preview, the exams, the old exams were out of 35, and this one was out of 25 because over the summer, the administration in the College of Engineering and Science told all of the engineering 220 teachers that we could not give an exam that took longer than our class period. So those exams were typically 2.5 to 3 hour exams. And so to be able to cut down on the time duration of them, I had to remove problems. Any other questions or comments about the administration side of things here? Probably the relationship between power and energy, current and charge, and all that kind of good stuff. Okay. So the reason why I'm hesitating here is because I don't know how to review that material without literally just telling you what's going to be on the test, which is not, I'm not going to do, to put it bluntly. So, for example, in today's lecture or whatever, the video lecture, which I believe covered both capacitors and inductors, there were a total of 8 equations, current and voltage relationships for inductors and capacitors, and then power and energy relationships for both conductors and capacitors. All 8 of those equations are fair game on your next exam, for sure. Whether or not I will ask you to specifically identify them or simply make you apply them through using a problem is still up in the air because I haven't started on that second test, but I can tell you guaranteed those 8 equations will be on your next exam. Emphatically, it will happen. Yeah, I will take your suggestion under advisement and think about ways that I can go about helping you review without telling you this, you know. All right, so possibly review. Equations before. All right, so is there anything else that you guys can think of that I could do to help you succeed further?
Dr. Hartman.
Yes, ma'am.
So one of the things that I struggle with, that I really struggle with on the test, is kind of knowing that there's so many possibilities of like equations we could use, like we could use the node analysis or we could use the mesh. It's just hard for me to choose one, I guess. And so that's the issue that I was having.
So I understand that sentiment, because that is one of the most difficult things about circuit analysis, is that there's never, or there's very unusually ever one correct way to work a problem. There's usually multiple correct ways to do it. And we're going to see that throughout everything. How I would approach that personally is, what I usually do is start by looking for what I consider to be the easy methods. So the first things I check off my list is simple things like Ohm's law and just direct application of Kirchhoff's current law or Kirchhoff's voltage law. If I don't see anything that will jump out at me where I can just use that one thing and get the answer that I'm looking for, then I move on to current division, voltage division, superposition. My last choices are always nodal and mesh analysis. Seeing or determining what is the best methodology to approach a particular circuit with is largely dependent on your practice, how much you're willing to practice, and your expertise. So one thing that I've noticed is that, you know, over the last couple of weeks, I slightly changed the paradigm, in as much as I didn't just say, all right, we're going to go over the in-class assignment and then get the hell out of here. I tried to leave you guys, you know, I went over a problem or two, and then I let you guys have some time to work. And I believe in the very first email that I sent out to the class explaining that Dr. Harbour was going to be covering while I was out with COVID or whatever, I had mentioned that the expectation was that you would attempt the in-class assignment prior to coming to class and then ask questions of me. And the questions that I was getting, let me use proper grammar there, is, how do I work this problem? Nothing specific to the problem, just, I don't know what to do and I don't know where to start. And that approach frustrates me to no end. Largely, and let me be clear here. That can be a genuine concern, like you may literally not know how to start or anything, but if you have no work to show me, I don't believe that you tried. And I'm not saying that that's what's happening with you at all, Nicole. I'm just saying a general statement to the class here. So like, if I have a criticism of you guys, it's that I don't see you actually watching the videos and actually trying the in-class assignments before coming to class. And that's kind of the contract or whatever that we have to work with in this weird situation, to where I only get 50 minutes with you instead of 2 hours with you. So to that end, I think me working more in-class examples and me giving you more examples online of things worked out may actually, if you're willing to take the time to go through them, may help you figure out, oh, well, when I see something like this, we go through the checklist and then, you know, I should approach it in this particular way versus that particular way. Like, even if you use nodal and mesh to do everything, which you can pretty much do in this class, may not be the most efficient method, but it'll get you through at least a whole lot of stuff here. Just recognizing that if you're looking for a voltage, nodal's probably correct. And if you're looking for a current, mesh is probably correct, because nodal gives you voltages and mesh gives you currents. So it's all about, you know, what you're asked to find. At the highest level, that's what's going to guide your decision on what circuit analysis application to go through with. Did I ramble too much, or did that make any sense whatsoever?
No, that absolutely made sense. So
Okay. Alrighty, so we have talked for 15 minutes about things. One thing I will be putting up on the Meta Moodle page later today, Eta Kappa Nu, the Electrical Engineering Honor Society, of which I am the faculty advisor, will be doing free circuits tutoring by Zoom for the remainder of the quarter, to help both, you know, you guys and people in Davis's sections and all that kind of stuff. So if you want more help and more access to people that are, you know, willing to go out of their way to help you, that's a place to get it. Unfortunately, I don't think I'll be able to participate just because I got 4 classes and program share crap to do. So that's one of the few things I'm disappointed about with taking over the EE department, is I don't get to do those anymore. I used to do 3 hours of tutoring a week, but my wife kind of wants me to be at home sometimes. So. All right, so in the vein of having more examples, let me start sharing the screen and all that kind of stuff. I have actually prepared 3 examples on inductance for us to look at today. Not from old tests, not from the in-class assignment, just other problems that we can look at so that we can kind of get our head wrapped around things, as it were. So let me move this stuff out of the way. All right, so this first example asks one fairly straightforward question, or at least it should be reasonably straightforward if you've watched the videos. If you haven't, then we'll have to discuss a few things. But it asks how much energy is stored in the 4 millihenry inductor. Let me see what is going on in chat. Whenever I work an example, can I go through my thought process? Sure. I can talk a little bit more about that. All right, so first things first, we are entering into into material where we are no longer going to be having DC circuits, which is going to introduce calculus-based relationships into our circuit analysis. And so things are going to get, they're going to get worse before they get better, to put it bluntly. We're going to have to do a little bit of calculus for a while to kind of figure out where things are at. So with this particular problem, one of the first things that I would do is I would look and see if it's a DC circuit or not a DC circuit, meaning my sources, are they constant or are they changing? What's the answer? So I only have one source in this whole circuit, the 2 amp source, and it is a DC source, which means this is a DC circuit. This goes into what's called a forcing function, which we'll talk about actually in about roughly 2 weeks' time. But effectively, if you put DC signals in, you should expect to get DC signals out. If you put sinusoidal signals in, you should expect to get sinusoidal signals out. And what I mean by getting a signal out is the voltage drops over components and the currents flowing through components will be of the same type as whatever you're injecting into the system, right? So the response, as it were, will be of the same form as the input. So we have a DC current source, and that's the only source in our system. So we need to know how to treat these inductors in a DC circuit. Does anybody remember how to do that, or any equations that might help us? So what I'm specifically asking about here are the relationships between current and voltage in an inductor, okay? So we have 2 potential equations. Let me put them in blue, all right? So our first equation is the current flowing through an inductor. And the current flowing through an inductor is equal to the inductance value. Sorry, I'm even getting this wrong. The voltage drop over an inductor, I was about to give you guys something awful, is related to the derivative of the current flowing through the inductor. And alternatively, we could express this relationship as the current is equal to the integral from some time where the current is known to some later point in time. Dang it, no, I'm rapid myself here. 1 over L, 1 over the inductance, excuse me, times the integral of the voltage over the inductor with respect to time, where X here is just a dummy variable for time, plus the initial condition on our inductor current. So we're going to look at this first equation for this particular problem. All right. So if my DC current source of 2 amps is the only excitation source connected to the circuit, what can I say about the current flowing through any of the other elements in this circuit, so the resistors and the inductors? If I have a non-varying current source supplying current to the system, I should be able to say pretty easily that the amount of current that's flowing through any of the other elements is constant. Is that fair? Anything jumping out at you that would make that not true, right? Kirchhoff's current law actually tells us it has to be true. If the only current going in is DC, then the only current going out of any of the nodes can be DC as well. So for the 2 millihenry inductor and the 4 millihenry inductor, what is the derivative of the current? 0, right? If we know the current isn't changing, then by definition, its derivative is 0. What does that mean for the voltage drop over each of those inductors? Pardon? It's also 0, exactly right. So what we can do in a DC circuit is treat all of our inductors like short circuits, because we know that their voltage drop has to be 0, and any amount of current that needs to flow through them can flow through them. So with that in mind, I'm going to redraw the circuit real quick. So this is my 15 ohm resistor here in the middle. This is my 10 ohm resistor here. So now let's talk about the 2 other relationships that we have for inductors, specifically power and energy, because we are looking for energy in this case, right? So our 2 other inductor relationships, and if you want the derivation for any of these relationships, they're literally in the video. That's why I do them. But we could say that the power absorbed by an inductor is always going to be the voltage drop across the inductor multiplied by the current flowing through the inductor, which will give us Li di by dt. So I've simply substituted in the equation I've underlined in orange for the voltage. And for the energy, not going to bother integrating this thing that's done in the video. The result is simply 1/2 times the inductor value times the current flowing through the inductor squared. So what we need to determine, the quantity that we need to find to determine the energy stored in the 4 millihenry inductor is effectively this current IL of T, which is going to be the exact same thing as this current flowing through our 10 ohm resistor. Is everybody okay with that? Makes sense, right? The current can't have changed or anything between the 2 different things. This is just a slightly different representation of our original circuit. So now that we have a better idea of what it is that we're trying to find, how might we go about doing it? Current division. Okay, so I was expecting either current division or mesh analysis, and current division, in my opinion, is the better choice because there's literally a current source connected to 3 resistors in parallel. This couldn't be a better place to apply current division than we've seen in this class. So to that end, I guess I can leave it like that. Our current IL of t, which is going to be a constant value, will be the 2 amps, the current supplied to our parallel resistive network, multiplied by, in our denominator, it's 1 over each of the resistive paths. So 1 over 5 ohms plus 1 over 15 ohms plus 1 over 10 ohms. And our numerator is going to be what? 1 over 10. So it's 1 over the path we want. So let's take a moment and calculate that. What did you guys get? All right, 0.545, so 0.54 repeating amperes. So we can plug that value directly into our energy equation, and we'll find that the energy absorbed by our inductor, in this case, is 1/2 times 4 millihenries times 0.545 amps squared. Is 595.041 microjoules. So before we move on, anybody have any questions about how we applied these relationships? So first, we identified that it was a DC circuit and then used that relationship and then used the current voltage relationships for an inductor to decide how to treat our inductor in the circuit, right? That's how we found out that since all of the currents are constant, the voltage should be 0. And so therefore we treat our inductors like short circuits. And again, that's only applicable for a DC circuit. Then we used our power and energy relationships to figure out what quantity it was that we're actually looking for in our circuit analysis, and then use that to calculate the energy. So hopefully reasonably straightforward. All right, so the next problem that I have might be a little bit more difficult. In fact, I think it's going to be significantly more difficult. That's okay. All right. So we are given the waveform of the voltage drop across an inductor. It looks like that it's a sinusoidal function only over really half a period, but it's well defined in as much as I've told you it's specifically 10 cosine pi t over 4 millivolts. And we are asked to determine the current for this particular waveform. So if we go back up to the top, which I'm not going to do, I'm just going to write down the equations again. We have the voltage drop over an inductor is the inductance times the derivative of the current, or we could do algebraic relationships and then some calculus and find that the current through an inductor is 1 over L times the integral from T naught to T of the voltage with respect to time plus some initial condition. So which of these two equations am I going to have to use to find the current based on what I'm given? The left one or the right?
I'd assume you'd use the one on the right since you know the sinusoidal.
Absolutely right. So we'll use the equation on the right because the voltage is well defined and we're trying to find the current. Notice in the problem statement that it tells us that I at t is equal to 0 is equal to 0 amps. That is this initial condition value, okay? So we are only looking at this over this specified interval, right? So we can say IL of t is going to be 1 over our inductor value, which is 50 millihenries. Let me put that in a little box like so, times the integral from the time when we know what our current is, which was 0 seconds, to some later point in time. And the reason why I'm doing it this way is specifically so that I will get a function and not just simply a numerical answer, because I want to know how it's behaving over this duration, okay? So we're going to integrate up to t, where t is just some number between 0 and really, really, really close to 4, of 10 times 10 to the minus 3, because I'm getting rid of my millivolts here, cosine pi t over 4. And actually this should be x, based on what I've been using. Plus 0 amps, where that plus 0 amps again is coming from my initial condition, okay? So this is the level of calculus I expect you to be able to do for the next few homework assignments in this next exam, is literally integrating and differentiating exponential functions and sinusoidal functions. Really anything past that is beyond the scope of what we're going to do in this class, okay? Alrighty, so the first thing that I usually do is try to get rid of as many constants and stuff and move them outside of my integrals to confuse me less and leave me with less opportunities for errors. So to that end, let's look at this 1 over 50 millihenries real quick. So 50 millihenries is 50 times 10 to the minus 3 henries, where a henry is a volt second per ampere. All right. If we pull out this 10 times 10 to the minus 3 volts, we can see first off that the 10 to the minus 3's cancel each other out, and the volts cancel each other out as well, right? So we're left with 10 over 50, or 0.2 amps per second. And then we have our integral here. So how do we integrate cosine pi x over 4? What's the rules for integrating? You guys have had calculus way more recently than I have. All right, nobody saying much of anything, so let's look it up. That's an easy way to figure things out. make sure I'm not going to divide by something I don't need to be dividing by, etc. So integral, let me share my screen here. Of cosine, and I'm going to say AX because there is a coefficient that's being multiplied by my variable here. So I'm going to have to do, I guess, the inverse of the chain rule inside my integration. So I want to make sure I understand how to do that. So the integral of cosine AX, I just want an integral table. Let's look. No, just give me an answer, dummy. All right, so it looks like this guy right here has it. So the integral of cosine AX is 1 over a sine AX. All right, so we're going to have over so what's a in this case? Pi over 4. So that means it's going to look like 4 over pi. What are the units? Not a trick question. Think about it. This is a quantity that's measured by time or multiplied by t, which is a variable representing time in seconds. So what do the units of this coefficient have to be?
Dr. Harvey,
Yes.
should it be 4 over pi?
Oh, you're absolutely right. Thank you. I wrote it not inverse, 4 over pi. Thank you. Let's get back to these units here. Okay. So what does the cosine function do? What is its argument? What is the argument of a cosine function going to be? An angle, right? It's either going to be in degrees, which is very, very rare, or radians, right? Radians is typical here. So I have something, radians something multiplied by seconds giving me radians. What's that something? Per second, right? So A here, this pi over 4, is what's called the angular frequency of the cosine function. It's something that we're going to be dealing with a whole heck of a lot in this class. Omega, where omega has units of radians per second. So since I have 1 over a, the units on this guy are 1 over per second, which is just seconds, because radians are inherently a dimensionless quantity. So this second cancels this second, and what I'm seeing is that my equation for the current is going to give me units of amps, right? I'm just following the units through here to make sure everybody knows what's going on, because it's very, very easy in these problems to mess up on the scale of our quantities. That's why I'm paying such close attention to the units. All righty, so there is our 1 over a portion, and then we have the sine pi x over 4, where we're going to evaluate x at 0 and t. So let me take a moment to erase this stuff here. difficult. Oh, no, not. Alrighty. So let's go through and look at a couple of these things here to minimize some of the math we're going to have to do. So we have in our numerator here, we have 1 times 10 times 4, looks like 40 to me, divided by 50 pi. And this thing has units of amperes. That's our coefficient outside of our functional thing there at the very end. So now we're performing, simply substituting things in here, right? So we're going to have sine pi t over 4. I'm simply substituting that in, the t for x. What's a sine of 0? 0. So minus 0. And so our answer is then 40 over 40 over 50 pi, which is 0.254 amperes. So 0.255 with rounding sine pi t over 4 amps, specifically over that interval. So 4, 0 less than t less than or equal to 4 seconds. Should be fairly straightforward at 0 everywhere else because we're integrating 0. So that's about as difficult as the calculus is going to get in this class. In fact, on exams and stuff like that, and you can see this from the old exams that I've posted, I usually give you simple linear functions and constant values, meaning that the waveform, I might give you a picture of a waveform, but it's composed of squares, rectangles, and triangles. If you can't tell me what the area under the curve of squares, rectangles, and triangles is, engineering might not be right for you. Okay, I mean, that may seem very harsh, but that's like 3rd grade math. So, I'm sure Dr. Hegat's going to hear about this. All right. Any questions regarding anything we did on this particular problem? So if we had, and we're running out of time here, so we're not going to be able to do a whole heck of a lot else. But what if we wanted to know the power? What could we do? So we know the voltage and we know the current, and we're trying to find the power. What do? You just multiply the voltage and the current, right? The power relationship, P is equal to I times V, is fundamental. That's always the correct answer. There might be other ways to do it, meaning we could take the power by doing the L times I times the derivative of I, which would be a lot more work than literally just multiplying this. Dang it, hold on, getting crazy here. By this. So don't forget about that fundamental power relationship too. 90% of the time, it's going to be the easier way to figure things out. Okay. Alrighty, the last problem that I have for us to look at is a fairly trivial one. And it's simply based on inductor combination. Okay. So again, I'm working under the assumption here that probably most of you did not watch the video, which hopefully that practice will change soon. But the general rule is that inductors in series combine like resistors in series, and inductors in parallel combine like resistors in parallel. Alrighty, so under that constraint, how are we going to solve for LEQ here? Any thoughts on how we might approach this? Pardon? Yeah, sure, find the node. That's a great place to start. So here's one node. There's another. There's another. There's another. Let's call this guy A, B, C, D, E, and F. So LEQ is simply the inductance seen between nodes A and D, right? So what can we do now? Yeah, we could, I mean, for this one, in my opinion, we've had enough practice to where we maybe don't need to redraw a whole bunch of things, but if somebody disagrees, we can absolutely do that. But we are absolutely in a place as well where we could just simply combine things too, if that's what you're comfortable with. So what I'm guessing Mr. Foyle is referencing is that we can see that both nodes C and nodes F are single points of interconnection between their respective inductors, which would mean that this 20 millihenry inductor and this 10 millihenry inductor are in series. And we could also see that this 20 millihenry inductor and this 10 millihenry inductor are in series. And both of those series connections are located between points B and E, right? So I have 20 in series with 10. What's that? 30. And I have another 20 in series with 10, so that's obviously 32. 30 as well. Let's say 32, but that might have been confusing. So to that end, between B and E, what do we see? 3 30 millihenry inductances all connected in parallel. What's the equivalent inductance of that? 10, right? So the way that it works out when things are of equal value is pretty easy. If there's 2 in parallel, it's half. If it's 3 in parallel, it's a third. If it's 30 in parallel, it's 1/30. Math is great. So from that, what's the overall inductance of this guy? 30. Okay, so the other way that I was talking about would be redrawing this thing. So if I put A over here and D way over here, to go from A to B, I go through the 10 millihenry inductor on top. Then from B to E, let's just put E over here for right now, I have the direct route of a 30 millihenry inductor. And then I have 2 other routes. I can go from B to C through the 20 millihenry inductor, and then from C to E through the 10 millihenry inductor. Or I can go from B to F through the 10 millihenry inductor, and so we'll put F right down here. And from F to E through the 20 millihenry inductor. and lastly from E to D through that bottom 10 millihenry inductor on the left-hand side. And so this gives us the exact same thing. Between B and E, we see 30 in parallel with 30 and parallel with 30, which is 10. And then we would see between A and D, 10 in series with 10 in series with 10, which is 30. So the bottom way that we did this is a little bit more time consuming, but it's just because this particular inductive network is fairly straightforward. All right, it's 1:20, so we have talked for the full 50 minutes that I'm trying to be allotted each time to speak with you guys. So hopefully, I don't know, maybe this format of more examples that are different and all that kind of good stuff will work out. If you have any more questions, comments, concerns about what I could be doing better in this class to help you guys succeed, feel free to shoot me an email or yell at me in the parking lot, or whatever communication you choose to use is fine by me. If you could, please wipe down your table before you leave so that we can get the next group of kids in here. Thank you very much.
Dr. Hartman?
Yes, sir.
My internet was messed up and I didn't log on until 12:33, and I think you missed my name.
All righty, I will take care of it in the roll. Thank you.
Thank you.
All righty. First, I'm going to take roll. So Garrett, for those of you on Zoom, please speak up when I call your name. Garrett Anders. Thank you. Brandon Bolin. Joshua Brack, I see you over there. Thomas Casey.
Here.
Thank you. Gifford Courtney, or Courtney. Okay. So is your first name Courtney or your last name Courtney? Okay, I got it mixed up here. Gifford. Alrighty, Paul DeSoler. William Drake. Jean Dugas, right there. Joshua Ekachukwu, I got you. Jonah Fitzgerald. Christian Gil Bustamante. Michael Hebert. Carrick, you're over there. Emma Coach, thank you, ma'am. Briley Marchand. Emma Michael. Shahara Pereira, thank you. Cameron Petrus.
Here.
Thank you. Alec Reddick. Colton Shriver. Leslie Sierra.
Here.
Thank you. Adam Swallow. Jillian Stalder.
Here.
Thank you. Jace Warren. And Kyron Wood. Gotcha. All righty. So before we get started today, I want to talk about the exam a bit. So the overall average among all three sections of Engineering 221 was a 63.77%, which I thought was fairly low because in my opinion, and you guys would probably think I'm a jerk, but it is my opinion, this was the second easiest circuit test I've ever made. Our section had an average score of 60.56 points, so literally half a point away from a failing class average. The minimum score was a 27, and the maximum score was a 105. There were 2 A's, 5 B's, 7 C's, 11 D's, and 23 F's. So not much of a bell curve, just an exponential growth towards failure. So what I want to talk to you guys about for the first 10 minutes or so, and it's what I talked about with the first class, is what can I do better, or what do I need to change to engage you guys more and help you to succeed in this class? So more difficult problems, that's what you said? Okay, I have had somebody in the first class suggest that very thing. So absolutely, I'm happy and willing to do that. My only potential problem with that is that a more difficult problem takes more time. And so let me talk for just a moment. So on some days, we have the lab assignments and we are extraordinarily limited in the amount of time that I can spend on actually covering material. And so what somebody in the first section here said was maybe also put up more example problems online as well. And so I might be able to do more difficult problems in that format on the lab days and stuff like that. I understand that that means that there's, well, literally no interaction with the students, which is really what I would want when working in a difficult problem, to figure out where you guys are messing things, or I don't want to say messing things up, but you know, not catching what I'm throwing, as it were. But that is a way that I think we can, if I do more example problems in class and then also do more example problems out of class and put up videos, if you guys are willing to watch the content, then I think it will be helpful. To that end, before I come circle back around to you guys, one thing that I have noticed, you know, over the past couple of weeks, I've been doing things slightly differently, in as much as I just haven't been saying, all right, so let's work the in-class assignment and then get on out of here. Usually, or at least several times, I think, I worked an example problem or two and then left you to your own devices to work on the in-class assignment. And what I had observed is that most of you had no prior work done on the in-class assignment whatsoever. And I believe in my very first email to you guys informing you that I was quarantining because of the coronavirus and that Davis was going to take care of things for the first few meetings, I thought I had explained that the expectation that I have of you is that you watch the video lecture and then you attempt the in-class assignment before coming to class. And it certainly seems like the overwhelming majority of students aren't doing that. So my biggest concern is that I'm going to spend my time and effort putting more examples online to be completely and utterly ignored while you guys fail miserably. So I'm happy to put stuff on there, but I need something from you too to say, you know, hey, we're actually going to use it, because I teach 4 classes and I'm a program chair and I have a second job as a design engineer over in Bossier. So me dedicating more time to this class, it needs to be reciprocated in you dedicating more time to the class as well. I don't think that's an unreasonable expectation. All right, so more in-class examples, more online examples, and more difficult examples. Anything else that I can be doing? Okay, nobody's saying much of anything. All right, so one thing that I want to inform you of, and I'm going to put this on Moodle today or over the weekend at the latest, is that the Eta Kappa Nu, which is the Electrical Engineering Honor Society, of which I am the faculty advisor, have agreed to do online via Zoom free circuits tutorings. I don't remember what day or days a week they're going to be doing it, but that is something that I'm going to post that you guys will have available, so that you'll have electrical engineering upperclassmen who've suffered through me on numerous occasions, trying to help you guys figure out what the hell I'm going to throw on a test and how to work problems and stuff like that. So I think that's a good resource that you guys can use. In the past, I did the tutoring, but unfortunately I don't have the time to do it now because my wife, you know, wants to see my face. All right, so any other questions, comments about what we can be doing better, or just general gripes and complaints about the test or anything like that we need to address before we jump into new stuff? Okay, cool deal. Yeah, and so just to be to reiterate that, you know, that's something that's we try to do it for free and as often as we can, so that you guys don't have to go spend, you know, even more money to learn this crap, when for a large majority of you, or maybe not a majority of you, but for most of you, you know, especially you civils, I'm looking right at you, and chemies, this is the literally only time you'll ever be exposed to it, and you just want to get the hell out of here, and I understand it. because if you told me that I had to go take statics again, I'd punch you. So, alrighty. So let's jump back into lecture mode then. Let me share my screen. So what I've done for today is I have prepared 3 example problems because I kind of felt what you guys were going to want to happen. Yeah, that's my fault. I got backed up, I think, in the spring quarter and just recorded 1 video over the whole deal. Today we're going to focus primarily on inductors, and then we'll focus largely on capacitors on Monday. Thank you, because I never know what day of the week it is. With that in mind, let's jump into some problems on inductors. So our first question asks us how much energy is stored in the 4 millihenry inductor. So one of the students in the previous section asked me to do a better job of effectively telling you what's going on in my head as I approach one of these problems and stuff like that. And I think that might be useful. So in this circuit, we have a 2 amp DC source that is supplying power, presumably, to the remainder of the circuit, right? So what do you think that means for, say, the current flowing through any of the resistors or any of the inductors? And what I mean by that is if we inject a DC current into the system, what is our expectation for all of the other currents in the system to be? Are they going to be constant? Are they going to vary with time, or no idea? They should be constant, right? So Kirchhoff's current law tells us that they should be constant. And so let's think about that for a moment, right? If I have a 2 amp DC source, let me change my pen color real quick. And it's supplying 2 amps of current into this node. When it branches off, it should still be constant values, right? So this is an example of what we're going to call a forcing function in about 2 weeks' time when we get into transient analysis, stuff like that. So what that really means is that if I excite a circuit with a DC source, whether it be a DC voltage source or a DC current source, my expectation is that the response, which is going to be simply the voltage drop over or the current flowing through some component in that circuit, should also be DC. If I excite my circuit with a sinusoidal response, which means I plug something into an outlet here in the wall, the expectation is that the voltage drop or current over the components in that system will also be sinusoidal signals, unless we have a rectifier or something like that, which converts AC to DC. But if I put a resistor through the pins of that outlet, and I needed to use a big one so that I don't trip a circuit in the building, and we took our multimeter and tried to measure the DC voltage across it, we wouldn't get anything because it's incapable of measuring that change. We actually have to use the AC voltage meter to see things. So in general, if we excite a circuit with a particular type of source, so a DC source, we expect our response to be DC. If we excite our circuit with a sinusoid, we expect our responses to be sinusoidal. If we excite our circuit with an exponential function, we expect our responses to be exponential functions, etc. All right, so with that in mind, that we should be expecting DC currents through all of the components in this circuit, let's look at the current voltage relationships for an inductor. So our first relationship says that the voltage drop over an inductor is the inductance value L multiplied by the derivative of the current with respect to time. And then we could do a little algebra in calculus and re-express this exact same equation as IL of t, the inductor current, is equal to 1 divided by the inductor value L from time t naught to t of the voltage drop over the inductor with respect to time, where I'm just using x as a dummy variable for time, plus some initial condition on my current, okay? So this is me getting away from saying integrating from negative infinity to t. Now I'm saying I know what it is at some particular time, and that's all taken care of in that guy. All right, so we have the current voltage relationship for an inductor. So let's use these relationships to figure out how an inductor is going to behave in a DC circuit, okay? So we talked just a moment ago that the current through both the 2 millihenry inductor and the 4 millihenry inductor should be constant in time. What does that tell me about their derivatives? Right, this guy right here needs the derivative of the current flowing through an inductor. It's 0, right? So the derivative of a constant is 0. So based on that, what is my expected voltage drop over the 2 millihenry inductor or the 4 millihenry inductor in this case? Also 0. So in a DC circuit, we can treat our inductors like they're short circuits, because we know that the voltage drop over them is 0, but whatever current needs to flow through them can flow through them. So I can redraw this circuit using that inductor model. So anytime I have a DC circuit, I'm just going to replace my inductors with wires. If I do that in this circuit, this is what I'm left with. All right. So now let's talk briefly about how that actually helps us determine the energy stored by the inductor in this circuit. And to do that, we're going to need to look at the power and energy relationships for an inductor. So the power, by definition, will always be the product of current and voltage. Can't get away from that. So it doesn't matter if it's a resistor, capacitor, inductor, transistor, whatever, it's always voltage times current. If we substitute in our relationship for voltage, we can see that we'll have Li times di by dt, okay? But I would say 80 to 85% of the time, I just simply go with the V times I relationship. That's the one that I find more useful, and it's actually the one that I see most students forget, which is crazy because you've been exposed to it since Engineering 120. For the energy relationship, we could suffer through the integration, and I think I did that in the lecture video, so I'm not going to do it here. Instead, we'll just get the result, which is 1/2 L times the current flowing through the inductor squared. So in order to determine the energy stored by our inductor, we are going to need to determine this inductor current, IL of t, which isn't going to vary with time. I'm just, making sure my notation matches. And that current is the exact same thing as the current flowing through the 10 ohm resistor in our simplified circuit. So how would you all decide how to solve for that current IL of T flowing through the 10 ohm resistor. So could we use mesh? And the answer to that question is absolutely. The better question is, should we use mesh? And so let me explain what I mean by that. Yeah, we have a 2 amp source in parallel with a bunch of resistors. Yeah, current division. This is a circuit made to apply current division to, right? This is the basic setup for current division. Nothing tricky, nothing fancy. So using current division, we'll have IL of T is equal to our source current, 2 amps, multiplied by, so in our denominator, it's always 1 over the resistance of each branch. So 1 over 5 plus 1 over 15 plus 1 over 10. What goes in my numerator? 1 over 10, right? So it's 1 over the branch we want divided by the sum of 1 over the branches. So take a moment and calculate that current and tell me what's what. Okay. All right, 6 over 11. Anybody else get that? All right, so that's 6 over 11 amps is 0.545 amps. So using this value, the energy stored by our inductor is simply 1/2 times our inductor value, which was 4 millihenries, times our current, 6 over 11 amps quantity squared. I get 595.041 microjoules. Just for those of you guys who. Yeah, so a Henry is a measurement of inductance, and a Henry is defined, that's literally what I was about to do, is define that unit for you guys because we're going to use it in a moment. So 1 Henry is equal to 1 volt second per amp. So if we use that unit definition there, we're going to have volt seconds per amp multiplied by amp squared, which means we have volt amp seconds. So a volt times an amp is a watt, and a watt times a second is a joule. So everything's hunky-dory. All righty. Oh, goodness. So any questions about that particular problem before we move on to the next one? I feel like that one's fairly straightforward. We discussed the different relationships between current, voltage, power, and energy for our inductors, which we'll put into application in the remaining problems we're looking at. Learned a little bit about how they behave, etc. So anybody got anything before we move along? All righty. In our next problem, the level of difficulty has increased a bit, okay? So I'm going to write down our current and voltage relationship equations again real quick here because I don't want to scroll back and forth. All right. So in this problem, we are given a waveform for the voltage drop over our inductor. And we are asked to find the current flowing through the inductor, given that the inductance is 50 millihenries and the current at T is equal to 0 amps. So the first question here that I'm going to ask of you is which of these two equations should we actually be using? The one on the left or the one on the right? Yeah, the one on the right. So the voltage is well defined, so that's the one we want inside the function. We're trying to determine the current. So to that end, there's something very that I want to make very, very clear here. And it's with regards to the what's called the initial condition on the inductor. So we're told that the initial condition on the inductor is at time is equal to 0, there is a current of 0 amps. That is literally what we're going to put as IL of T naught. So T naught just represents some point in time where we know how this element is behaving. And that point in time happens to be 0 seconds in this particular example. So T naught is 0 then, which is going to help us define our limits of integration in a moment. And there we go. All right, so using our equation, we are going to have 1 over 50 millihenries, where a millihenry is 10 to the minus 3 volt seconds per amp. And I'm going to be very, very particular about the units here, because on these types of problems, particularly when doing the integration, it's very easy to get the scale wrong. So you might get a number in milliamps that's supposed to be in amps or supposed to be in microamps or something like that. So I'm going to be real nitpicky about the units here. So I'm just giving you a heads up. And I suggest that you do the same in your homeworks and stuff like that. You may have been ignoring units up to this point. It's probably a really good idea to start messing with them. All righty, then we have our integral from 0, and I'm integrating to T here. Not 4 seconds or anything like that, because I want to see how this guy varies with time. So I want my answer to be a function, not a specific numerical value, right? So if I integrated this from 0 to 4 seconds, which is the upper bound of when this waveform isn't 0, it's going to give me a number, but it's not going to tell me what happened between 0 and 4. So that's why I'm integrating with respect to time. I just wanted to be clear about that. Then we have our voltage waveform. So that's 10 times 10 to the minus 3 volts times cosine pi t over 4. Oh, it should be pi x over 4, excuse me, using the dummy variable that we've been using. dx plus our initial condition of 0 amps. One other thing that I want to point out here is that the initial condition is not inside the integration. Okay, so don't integrate that too. I just want to be really clear about that. All righty, so I'm going to pull out my constant value of 10 millivolts. So if we look at the units here, that means this 10 to the minus 3 cancels this 10 to the minus 3. This unit of volts cancels this unit of volts. And so we're left with something amps per second. So how do we integrate cosine pi x over 4? This is the level of difficulty of integration you'll see in this class. Sinusoidal functions and exponential functions will take derivatives and integrals of. Anything past that is really beyond what you're going to see for a current or voltage waveform, so it's none of my concern. Anybody remember how to integrate cosine of AX?
4 over pi. Sine pi x over 4.
You're absolutely correct. So the rule here, integral of cosine alpha x dx is 1 over alpha sine alpha x plus c for an indefinite integral. So 1 over alpha in this case is exactly what the woman whose name I missed said, but it is 4 over pi here. Now, here is a question for you guys. What are the units on this coefficient? So we're looking at this variable alpha, or not a variable alpha, but a number alpha. X here is time, presumably measured in seconds. We don't have any reason to think it's not measured in seconds here. So what is the argument of a cosine function? So what does a cosine function act on? Angles, right? That's cosine, all of your trigonometric functions. So alpha is what's known as the angular frequency. Something that we're going to be dealing with an awful lot in this class. You may, in this class particularly, we're going to see it as omega times time. Angular frequency, let's just call it omega because that's what we're going to be doing. And it has units of radians per seconds, because when we multiply that omega times our time variable, it gives us an angle, right? So radians are a dimensionless quantity, which means the units of alpha in this case are per second. So 1 over alpha would then give us units of seconds. And so this second cancels this seconds, and we can now pretty easily see that our unit for whatever is going to come out of this thing should be amperes, which is what we would expect for current. So I just wanted to be very, very particular and clear about what was going on with the units in this, because it's a very, very common place to trip things up and wind up with weird things. Then we're going to have sine pi x over 4, and this will be evaluated at the limits of our integration, which are t and 0. So let me take a moment to erase this ancillary material. There we go. So if we do our math here, we have 1 times 10 times 4, so that's 40. In the numerator, 50 times 1 times pi, so 50 pi amperes, multiplied by sine of pi t over 4 minus the sine of 0. What's sine of 0? 0. So this guy just goes away. So what we're left with then, if we do the math, 40 over 50 pi, is 0.255 sine pi t over 4 amps. And this is true for t greater than or, sorry, 0 less than or equal to t less than or equal to 4 seconds. And if we looked at our waveform, it should be fairly obvious that prior to t is equal to 0, our current had a value of 0 because we're integrating 0. And after t is equal to 4, we also have a value of 0 because we're, again, integrating 0. So yeah, like I said before, this is about as difficult as the calculus is going to get in this class, to be entirely honest. On your exams, and you can verify this by looking at the old test that I've put up. Typically speaking, when I ask you to perform integration on a graphical problem like this one was, it's rectangles and triangles, right? So you're going to be taking the area under the curve of rectangles and triangles. So a rectangle is effectively base times height. Triangles is 1/2 base times height. If you don't know that, well, you do now, assuming they're right triangles anyway. So the level of calculus that you're going to be expected to do on the exams is largely going to be adding triangles and rectangles, or you can put it directly in your calculator and run. And for those of you, make sure, if I give you omega and it's in radians per second, make sure that your calculator is set in the radians mode so that you get the right answer. Right? That's something that can trip people up. Looking at you, sir, you figure out how to use your calculator yet? Awesome, great. So, not to pick on you too much, but yeah. Alrighty, so any other questions regarding this particular problem? Everything seemed relatively okay. Alrighty, so the last thing that I have prepared is a problem where we're asked to find the equivalent inductance of a inductor network. And so I would like to talk about the rules governing how we combine inductances real quick. In the lecture video, there's a derivation of how it's done. I'm not going to worry about that too much here. We're just going to talk about it. And so the general rule is inductors in series add like resistors in series. And inductors in parallel add like resistors in parallel. So with those two rules in mind, let's take a crack at figuring out what the equivalent inductance of this network is. So what can we do to start this thing off? Sure, that's a good way to start. That's where I typically start as well. So if we identify our nodes, we have this guy, this guy, this guy, and so I'm going to call, just for the sake of argument, A, B, C, D, E, and F. So now that we have labeled and identified and labeled all of our nodes, what we're really looking for here then is the equivalent inductance seen between terminals A and B of this network. So how can we, what's the next step in our approach? Alrighty, so what Mr. Ekachekwu, I think if I'm pronouncing his name even closer right, has saying is that we can observe that node C is a single point of interconnection between this 10 millihenry inductor and this 20 millihenry inductor, so we could combine them. What you might also observe next is that this 20 and this 10 are also in series, right? So what is the total inductance seen between nodes B and node E? So we have this 30 in parallel with 2010, which is another 30, in parallel with 20 plus 10, which is additionally 30, right? So we have three 30 ohm inductances in parallel with each other. What's the equivalent inductance of that? 10, exactly right. That's the beautiful thing about resistor combination and stuff like that, especially when you have identical resistances. So if you have two identical resistances in parallel, the answer is 1/2 of one of the resistors. If you have 10 identical resistance in parallel, it's 1/10. If you have 137, it's 1/137, right? Follows very, very straightforward. So if the inductance seen between nodes B and E is 10 millihenries, then what is the inductance seen between nodes A and D? So it's 10 plus 10 plus 10, okay? So just for the sake of argument, for anybody that may not have followed exactly what went down here, let's write things out in a little bit more formulaic way. Here we go. So I'm going to put A on this side and D on this side. Between A and B, we have a 10 millihenry inductor. And then to go from B to E, we can go directly, which is the 30 millihenry inductor, or we can go through node C, which is a 20 millihenry inductor, and then to E through a 10. Or we could alternatively go from B to F to E. So from B to F is a 10. From F to E is a 20. And finally, from E to D, there's only one available path, which is through this 10 millihenry inductor. Oh my goodness, my nose is itching like crazy. So hopefully this makes it more obvious that it's just 10 in series with 3 parallel 30 millihenry in series with another 10. So LEQ is 30 millihenries. All righty, so that's all that I had prepared for today. So do you guys have any questions about anything that we covered today, or any other comments that you want to talk about regarding the exam or anything like that? We got a couple minutes. Mr. Brack, how can I help? So to review your test, I need to speak with Davis. And so here's the potential issue. I have no problem with any student coming. I know that my office hours right now are on Zoom, but I'm usually on campus from 7:30 to 8, thereabouts, on Monday, Wednesday, Friday, till before I walk over here to take my test. So if you want to come by and review your test, I will allow you to do that. I've been asked if I'm just going to release the test and a solutions guide or the answer sheet. And the answer to that is I really don't know. And I say that because it's looking very likely, due to scheduling concerns and stuff like that in the EE department, because we're short staffed, that I'm not going to get to teach circuits for the remaining, for the rest of this academic year. And so I don't want to release this test and then screw over Dr. Harbour into having to make entirely new tests and all that kind of jazz. I usually do that. I make a new test every quarter, but I don't know that he's willing to do that. So I don't want to just shoot him in the foot before he even starts taking over handling all that crap. So is that an acceptable answer? So you can come by, shoot me an email first to make sure I haven't like wandered off or something like that, because that happens quite a bit. But I'm usually around somewhere. And yeah, I'm happy to go over your exam with you whenever you want to do it. Yeah. Well, let me know that you're coming so I can clean things up, because right now it's a hot mess. From 7:30 to 11. No, like my normal office hours, I should be there, but shoot me an email first to make sure that I'm actually there. Or pop into my Zoom office hours and be like, hey, I'm on my way. That'll also work. And you'll also be able to see whether I'm in my regular office or my home office. So if the walls are yellow, I'm at tech, and if the walls are gray, I'm at my house. Any other questions regarding the exam or anything else? All right, we get to knock off a couple of minutes early. So please, somebody at each table, wipe it down before you get out of here. And I'll see you on Monday, where we'll talk about capacitors.